Bismillahirrahmanirrahim. Dear students, in the previous lecture, the recursive calls and behavior of stack on these calls been discussed through different examples. In today's lecture, the types of recursive calls will be explored along with related examples. As stated in the last lecture, that a function that is defined in terms of itself is called recursive, and this property is known as recursion. All types of recursive calls follow this rule. Moreover, all types of recursive procedures deploy stack during their invocation and processing. Ladies and gentlemen, starting from the direct recursion, the other types include indirect recursion, nested recursion, excessive recursion. All of these types will be discussed in today's lecture one by one. Dear students, the tail recursion uses only one recursive call at the very end of a function implementation. The recursive call is not only the last statement, but there are no earlier recursive calls, direct or indirect. There are no statements left to be executed by the function when it is applied as tail recursion. It is depicted in the snippet of tail function call with no return value. The non-tail recursion may contain other instructions after the recursive call. Dear listeners, due to the structure of a tail recursive function, only the last recursive call is kept on the stack, limiting the space of the running program, while with non-tail recursive functions, each recursive call is kept on the stack until the end of the evaluation. This is shown in the reverse recursive call that ends with the cout instruction. Dear viewers, this slide depicts the behavior of non-tail recursion, showing changes on the runtime stack during reverse call execution. Dear students, another type of recursion known as indirect recursion makes use of more than one method. For instance, a directory traversal program where one method is for navigating the hierarchy and the other for processing the files. If the file turns out to be a directory, then the original process folder method is called, and so on. This procedure is depicted in the diagram below, where more than one method are called. Ladies and gentlemen, the nested recursion is a recursive function that passes the parameter as a recursive call. It is basically recursion inside recursion. A well-known example of such type of recursion is an Ackermann function. As you can notice, the third statement of the diagram depicted in this slide, that the function is defined recursively and it is further recursion within recursion. Dear students, an excessive recursion is a recursive procedure containing more than one call to itself simultaneously. A very well-known example of such a recursion is the Fibonacci function. This function is defined recursively in this slide. Ladies and gentlemen, to further understand the concept in a better way, a particular case of recursion is described, known as Towers of Hanoi, in which 3 pegs are given. These pegs are labeled as beginning, auxiliary, and ending. The beginning peg contains n number of disks placed in a decreasing size from bottom to top. The auxiliary peg, positioned in the middle, is involved as the helping peg. The Towers of Hanoi problem has the objective to move these n numbers of disks from beginning peg to the ending peg in minimum number of moves. Moreover, ladies and gentlemen, the Towers of Hanoi strictly follows two types of rules. The first rule describes that only one disk may be moved at the same time. Specifically, only the top disk on any peg may be moved to any other peg. The second rule mentions that at no time can a larger disk be placed on a smaller disk. The Towers of Hanoi problem belongs to the exponential efficiency class, as it takes 2 raised to the power n times the movements of the n number disks. Dear viewers, this slide exhibits the Towers of Hanoi with 3 disks. Initially, the beginning peg, which is in this case labeled as A, contains 3 disks. The process of moving the disks progresses until the end peg, which is labeled C in this diagram, contains all the 3 disks. The whole procedure of moving the disks step by step is shown in this diagram. Dear students, the general solution to this problem states that if the disks are greater than 1, then move the top n-1 disks from the beginning peg to the auxiliary peg. Move the top disk, which is single in number, from the beginning peg to the ending peg. Finally, move the top n-1 disks from the auxiliary peg to the ending peg. Dear viewers, this slide mentions the recursive function calls in case of Towers of Hanoi. It must be noticed that each of these 3 subproblems may be solved directly, or if essential, they may be solved by making recursive calls to themselves, as the case of the original problem. The exact movements are 1 less in 2 to the power n moves of the disks. In this slide, the recursive calls are depicted for 4 number of disks that take 15 moves to accomplish the objective. Dear listeners, finally, it is imperative to note that the recursion is a special case of a general phenomenon in programming called reentrancy. Reentrant code can be safely re-entered, meaning that it can be called again even while a call to it is underway. Reentrant code keeps its state entirely in parameters and local variables, and it doesn't use static variables or global variables. Moreover, It doesn't share aliases to mutable objects with other parts of the program or other calls to itself. The direct recursion is one way that reentrancy can happen. For instance, the factorial method is designed so that factorial n minus 1 can be called even though factorial n hasn't yet finished working. Indirect or mutual recursion between two or more functions is another way where A calls B, which calls A again. Indirect or mutual recursion is virtually always intentional and designed by the programmer, but unexpected mutual recursion can lead to bugs. Dear students, this was our final lecture on the topic of recursion. For further details and studies, you are hereby advised to consult 6th chapter of Data Structure book by Lipschutz. Till next lecture, stay home, stay blessed, keep learning.